Okay, we'd like to start. So next speaker we have Jonathan Pila from the University of Oxford, and he tells us about Ax-Schanuel and exceptional integrability.
Okay, thank you. So I'd like to thank Gareth Jones Airline Company and my co-organizers for the opportunity to speak here. It's a little bit not quite on the topic. There's no liminality and there's not much Diophantine problems, but it actually, I think it fits in quite well with things that we've heard, particularly from Ben and a bit from Thomas about Ax-Schanuel. So this is about Ax-Schanuel and a very classical topic of exceptional integrability. And so this is joint work with Jacob. Zimmerman. So, and part of the motivation was to see somehow for which functions you could expect an Ax-Schanuel, but another motivation was the Massa-Zanier work on elementary integrability, which they connect to Diophantine problems of Zilber-Pink type, and they study. Well, that is sort of a bit mysterious in a way where that connection comes from, although it's also very classical. And I think we're able to make an Ax-Schanuel connection there. So elementary integrability. Is a very classical topic. It's also called integration in finite terms. And the question there is somehow, when does a given function have an elementary primitive or antiderivative? And elementary means that you can build it up in a sort of in an explicit write-downable way using the logarithm and the exponential and algebraic functions. So for example, the subject really goes back to Liouville in 1835, who showed that things like e to the x squared and the logarithmic integral, that these are non-elementary. You can't write down closed form functions in terms of log and exponent algebraic functions that have those functions. So that these are really new functions in that sense. So I want to give a definition. So somehow the idea is that you can't write them down explicitly, but explicitly is going to include using solving algebraic equations and functions. So that's not so explicit. And I want to write a definition here. So a definition.
Yeah, the pen is.
Yeah. Tired pen syndrome. Definition. All right. So, all right. So let Z be a function of X. It's regular on some disk delta in the complex numbers. And we'll call Z of X elementary if there is a finite sequence non-constant functions, like pairs of functions, xi and zi. So they're all non-constant functions on the disk or on a smaller disk, possibly with the following properties. One, for each I, dzi dxi is 1 over xi. So zi is determination of the logarithm. 2, for each I, either xi or zi is algebraic over the field with X and the previous things.
These are or conditions, right? Either one, they don't all work.
Yes, they all have with what?
It's exclusive.
Oh, yeah, well, both is not going to be useful, right?
So what I mean is, you don't, oh, no, I'll let you
What,
say. Yeah,
well,
sorry.
at least one of xi or zi would that,
Yeah,
I think it's just saying that either one holds or two holds.
they don't all have to hold, one and two don't have to hold.
oh yes,
right?
1 and 2 have to hold. For each I, zi dxi is 1 over xi. So zi is always a logarithm of xi.
Yeah.
And for each I, 1 of xi or zi is algebraic over the previous field. Well, both wouldn't be helpful, because then the next one, and then you're just making algebraic extensions.
It's really nice for us to see the feud between US semantic and British semantic.
At least one of, at least one of xi and zi. Is it, but it could be both. I mean, both wouldn't be helpful.
It's a new,
Sorry,
it's a new mathematical concept.
three. And 3, right, finally, Z is algebraic over the whole field up to xk and zk. Right, so the idea is that you start with x, if you like, with the field cx, and then you adjoin something algebraic, which could be the x or the z, and then you either take its logarithm or its exponential, and then you can take more algebraic things and their logs and exponentials, and eventually you get something that z is algebraic over. So that's what it means for a function to be elementary. And so then, if you like, Liouville proved that this function and this function, they're not elementary. But on the other hand, for example, you have examples like this. I think this is an example of due to Abel, but I got it from the Massezania paper. This is equal to this integral is elementary. Well, that's the same square root. And then we've got x squared plus x minus 2 minus that square root. So that integral is elementary. All right, so so for the most of the talk, I'm going to be talking about Abelian integrals like this one. So these are sort of going into wider things. Now, this integral, of course, can be written as an integral of a meromorphic differential on a curve. Let's call it 5x minus 1 over y dx, where y squared equals that stuff. So that's a meromorphic differential on an elliptic curve. And these Abelian integrals can sort of always be written in that way. Now, I want to write the theorem of Liouville. So this was the theorem he proved to solve that problem. So this is Liouville's theorem. So let F be a field of meromorphic functions of T in some disk, the complex numbers, closed under D equals D by dt. and X is an element of this field, then if dz equals X with Z in some elementary extension, should have said elementary differential extension field, differential, closed under d by dt, then there exists x1 to xm and v in F, and some complex numbers ci, such that x is equal to the sum of the ci times dxi over xi, I equals 1 to m plus dv. Right, so this x, in other words, sorry, z. No, then x. And then z, of course, is then just the sum of these logarithms plus this, plus v. So we're saying that if this element x in any differential field of meromorphic functions has a primitive in any elementary extension, then in fact you can get it just by taking logs and adding a derivative. You don't need x. Right. So, right. So Hardy in his book 1905, discussing the integration of algebraic functions, said that no general method has been devised by which we can always tell, after a finite series of operations, whether a given integral is really elementary or elliptic or belongs to some higher order of transcendence. So later, Risch, in 1970, he gave kind of sketch of this algorithm, and really the full proof only came out this year, 2022, in an edited book on this subject of symbolic integration. He gave an algorithm to decide whether any elementary function has an elementary integral. And a key point in this determination is that a certain divisor you construct from the function has to be torsion in a Jacobian. So there's an arithmetic condition that comes in, and which the arithmetic condition is very classical and goes back to, I think, to Abel even. And Masser and Zania, in a series of papers talking about relative Riemann-Mumford problems, but they wanted to study the problem of when, if you have a one parameter family of abelian integrals, so here alpha is some algebraic function of x and t, but we consider it as a family over t of abelian integrals. And the question was, or rather, the conjecture had been made somewhere that if there could only be finitely many values of t for which this thing was elementarily integrable, unless it was identically elementary, so somehow generically elementary. And they refute that conjecture, and they give specific examples where there are infinitely many specializations, but it's not. Again, where? Masser and Zania. Masser and Zania. It's a wonderful paper in Acta Mathematica, maybe 2020, the end of this. I mean, they did a series of papers on these relative Riemann-Mumford problems, and it's really wonderful. They explain how they were just on the cusp of proving that they never exist. And then, because they had all these, they built up these very stringent conditions, and then at the end of the day, there they are. It's really wonderful. I didn't write down the example. I mean, there's a completely explicit example.
Sorry, would it happen on a sort of positive measure?
No, no, it happens countably often on a set of countable algebraic numbers. I mean, they characterize absolutely. It has to be on an elliptic curve. It has to be an elliptic curve with complex multiplication, and it has to be a divisor, and it has to. It's really you start building up these conditions, but it's a countable collection of algebraic numbers.
Maybe it's worth saying that in some sense, the T's range over the points of an elliptic curve, which has to be CM, and the points at which it's elementary are the torsion points of the elliptic curve, and that's the only case.
Right. So what we wanted to do was rather somehow expand the definition of elementary and really ask when can one abelian integral be integrated in terms of some other abelian integrals. So an abelian integral is the primitive of an algebraic function. It's just, yeah. So so our problem really is this. Let me put away that. I'll put away that. So when can let me start the sentence again. So we're gonna consider. So we're integrating algebraic functions. So the algebraic function is given by some irreducible polynomial. So let's say that A is in Cxy, irreducible. And we've got, so that defines an algebraic function, alpha of x by A of x and alpha of x equals 0. And then we want to consider Z is the integral of alpha of x dx. On the other hand, we're also given some other set of B's, which are also irreducible polynomials in two variables, and which define some algebraic functions. Let's say bi of x, beta I of x equals 0. They define some functions. So we want to know when can you integrate alpha x, if you like, using a set of beta i's. And in other words, so the definition will be when is there a sequence? So let me put it here. When is there a sequence of xi's and zi's, say I goes from 1 to k, say, all regular functions on some disk that you may need to make slightly smaller than the original disk. And what we want is one for each I Zi with respect to xi satisfies the differential equation of one of those b's for some j, or for some bj in the set of b's.
Polynomial?
These b's are polynomials.
Polynomial, but they're not nothing. You're putting in the derivative, but it's nothing more differential than just an algebraic equation.
It's just an algebraic equation. I'm just saying dz dx is algebraic over x by this specific. That's all. Yeah. Yeah, that replaces the condition. That just replaces this condition. And then the next condition, let me write it with an either or. Either xi or zi is algebraic over the previous field. And finally, 3, Z is algebraic over everybody, over the full field. So it's just the analog of this definition. And we call this is the exceptional integrability. So exceptional is supposed to be this word that somehow sounds like elementary, but it's more general, okay? This is the exceptional integrability, if you like, of alpha, the algebraic function alpha, by means of the algebraic functions given by the B's. Right, and so what we're going to do somehow is give an Ax-Schanuel connection with this situation. Then there'll be a criterion and a decision procedure for deciding this given A and B. And when I talk about algorithms, I'm always going to assume that we're working over a finite type explicitly given field, not complex numbers. And we can also give an answer to an interpretation of this question of Hardy about when is the function elliptic. Right, so that is the definition. So we've already heard about Schanuel's conjecture, and we've already heard about Ax-Schanuel. I might just write down Ax-Schanuel somehow the way I want to think about it. So Ax-Schanuel, this will be a version just in one variable. Ben's version had several variables. So we let x1 up to xn be regular non-vanishing functions of some variable t on the disk delta in the complex numbers. And z1 up to zn will be some determination of their logarithms. So what I mean by that is that dzi, the xi equals 1 over xi. It just satisfies that differential equation. And then the conclusion is that the transcendence degree over C of the Z1s up to Zn and the X1 up to Xn is at least n plus 1. So there are n pairs of functions. The transcendence degree is n plus 1 unless the Zi's are linearly dependent over Q mod constants. So some rational, non-trivial rational collection combination of the Z's is a constant. And I just want to note the plus 1 term here. This was the rank term in the way Ben put it. Here the rank is 1 because it's functions of one variable. But the point is that when you have just n equals 1, and you've got one function and its logarithm, the transcendence degree is 2. So there's sort of, there's a plus 1 there. So this theorem is due to Ax from 1971. That's the functional version of Schanuel's conjecture. And in 1972, he gave a slightly different proof and extended it to complex semi-abelian varieties. And later, in 2009, Jonathan Kirby gave a differential field version of that. Somehow, this is really in fact about this differential equation. Now, Bertrand in 2008 noted that in fact Ax's proof works for a more general class of connected commutative complex algebraic groups, namely the ones that have no vectorial quotient. Now, I'm sort of not going to go into much details about the proof, but when you study abelian integrals, this leads to generalized Jacobians. If you study regular differentials on an algebraic curve, so all of these abelian, well, I've lost them all now, but when all of these integrals of algebraic functions, you can consider to be integrals of some differential on a curve. And when this differential is regular, you're going to end up in the Jacobian, which is semi-abelian, even abelian variety. But in general, when these differentials are simply meromorphic, then you end up in the world of generalized Jacobians. And sometimes these are not no vectorial quotient groups. Sometimes they have vectorial quotients simply because in the moduli that you consider the differentials, there may be exact differentials. So there may be differentials in some finite vector space you're considering that actually have an algebraic integral. So, and that gives you a vectorial quotient in the group. So we had to make a correction for that, and I'm going to state it now. So the point of this theorem, actually I was wondering let me write it down. So the point of this theorem is that there'll be an Ax-Schanuel just for some individual abelian integrals. They don't have to be a complete set of any functions to any modulus on any particular curve, but there'll just be a bunch of individual abelian integrals. So let me state this now. Now, in the application, there's sort of A's and B's which are distinguished. And so here in the theorem, I'm just going to have A0 and A1 to AK. But later, we should think of A0 as being the A, the function we're trying to integrate. And these A1 up to AK, they're the B's that we're trying to integrate with. So these are some irreducible polynomials over C. And now we'll suppose that Xi and Zi, non-constant regular functions of T on some disk in the complex numbers with AI, Xi, dzi, dxi equals 0. Just let me note, going back here in our definition of exceptional integrability, each pair Xi, Zi satisfies one of the equations with Bj, but these J's could be repeated, right? You can use the same integral like you in the elementary case. Well, in the elementary case, you have to use the same differential equation over and over. We're allowing several of those, but you can reuse them. And so I'm not saying that these capital A's are distinct. They're just, maybe I should, it's just a list. It's not a set. It's just a list. Anyway, each Zi with respect to Xi satisfies the corresponding differential equation. Then the transcendence degree over C of X naught up to Xk and Z naught up to Zk is at least, well, there are K plus 1 pairs, so it's K plus 1 plus 1. Unless there is a linear relation of the Zi's, possibly plus some algebraic functions equals 0. Ci in C, not all 0. And the gamma i's are algebraic, and we know rather more of them. We know a finite dimensional vector space in which they live. So let's say to a suitable modulus. We know their poles.
Can you just collect them all into one?
You could.
Well, I think gamma I is algebraic over Xi, right?
Right. Yes, that's right. Gamma I is algebraic over Xi. Right. No, that's right. So later, right. Gamma I algebraic over Xi. And to a suitable modulus. Right, later we'll be able to collect them. And in fact, in this statement, well, so we know rather more about this relation, that this relation is a coset relation. It's a relation, so somehow I'm not going to talk much about the proof, but so each one of these xi's and zi's we think of as defining some differential on some curve, xi, omega I on xi, and we put that in a suitable vector space to allow for the poles, and that gives us a generalized Jacobian. So this, if you like, becomes a locus in the generalized Jacobian and its universal cover. And then, like the usual Ax-Schanuel, the conclusion is that the zi's lie in a coset, in the translate of a coset. And so this relation too will be a relation on the zi's that comes from a coset in this product of generalized Jacobians. So I wondered, I mean, Ben gave us a list of Ax-Schanuel theorems, and I wonder, this is probably covered. Where's Ben? There. So this is probably now covered. This would follow also from your theorem, would it not? Would sort of have to.
Yeah, but the deduction of this from our theorem would be probably the same with the deduction of it from our Ax-Schanuel for generalized Jacobian.
Right.
Our theorem hides all the specifics in the group. Sorry, Ben, I'm answering for everybody now.
Yeah.
Well, no, I just, well, yeah. But, right. Anyhow, so I already consider myself to have given a sketch of this proof. You take a suitable product, you realize each of these Abelian integrals implicit here as actual Abelian integrals of a meromorphic differential on a curve. You take suitable generalized Jacobians of those curves. You take the product of those. In that you have some, you've now got x's and zi's functions in this product of Jacobians in its cover. But the point is that and then you have an Ax-Schanuel there, but the point is that Ax-Schanuel, if you like, relativizes and comes down to just these given functions, even if they were just k+1 Abelian integrals on k+1 totally different and unrelated curves. The sort of the Jacobian is, this generalized Jacobian is comes in, but then if you like goes away. Although you can't really understand this relation without knowing that it comes from some coset. So back to exceptional integrability, what does this tell us? So back to the exceptional integrability. So let's suppose that the integral of alpha x dx, where a of x alpha x is 0, is, or let's say z equals that, is exceptionally integrable using some b's. Using some via some sequence via x1, z1 up to xk, zk. So what happens, you've got all these functions. And you compute the transcendence degree of all these functions. And what do you have? Well, you have X, so that's transcendence degree 1. And then out of Zi and Xi, one of them is algebraic over what you had already. So the transcendence degree is both this 1 plus one of each of those pairs, so that's K plus 1, and then Z is algebraic over the whole lot. So you get at most K plus 1. But there are K plus 1 pairs of Abelian integrals here. And so you fall short of this required number. And that means that you end up in this exceptional case. And what that means then, so let me just replace, so let me replace this now. The theorem if alpha of x is exceptionally integral using, let's say, these BJs, then there is a sequence of functions x1, z1 up to xk, zk with 1 for each I, or just the condition we had before, that the zi, dzi, dxi, whoops, dzi, dxi satisfies one of the equations, one of the differential equations, but now 2 prime each xi is algebraic over x.
That's like the logarithm condition.
It's like the logarithm. That's exactly right. That's exactly right. That's what I've been taking up to reveal here, except I've screwed it up by putting this in the wrong board. Because this was our definition that it said that either xi or zi has to be algebraic, but the conclusion is actually it has to be xi. And 3i, not only is z algebraic over all of that, but it's actually linear. Z is linear, let's say modulo exact, suitable exact things, exact algebraic in the zi's. So that is what Ax-Schanuel, if you like, is improving this condition to this condition. Now, I'm afraid I wanted to have all these things on the board at the same time, but Liouville's theorem is rather more precise, because here it says that this z, this didn't have to be an Abelian integral. This was just any x in the differential field that has a primitive in something elementary. So it's stronger. On the other hand, our theorem is more general in the sense that we don't really need this. Well, the Ax-Schanuel operates just under the condition transcendence degrees fall down, and it doesn't have to be because each extension was degree 1. So it's a little bit more general in that sense. Exact means integrals of algebraic integrals of algebraic functions. So exact, I mean, yeah, exact differentials, exact meromorphic differentials. But and to suitable moduli. And you can give kind of a rather nicer formulation of this condition. So, well, as I've said, each of these, instead of just being an integral of an algebraic function, you can view it as an integral of a meromorphic differential on a smooth curve. So we have exceptional integrability of some z naught. Well, let me just write integral of omega naught, but this will be on some curve, smooth projective curve x naught with the choice of a base point somewhere in terms of some integrals of other algebraic functions, meromorphic differentials on smooth algebraic curves. If and only if omega naught is in the complex span of differentials, which are trace images of the omega i's. So this is on a curve x naught, xi. Trace images of correspondences of the omega I under correspondences on x naught cross xi for all the i's, well, modulo exact forms. And these exact forms, we somehow know how to narrow them down to finite dimensional space. And so then this can be used as the basis of a decision procedure. That you can decide that. And further, you can also decide, so theorem, given alpha x some algebraic function, one can decide whether alpha x dx is exceptionally integrable using the primitives of all meromorphic differentials on all elliptic curves over C. So, yeah, I guess so. We have a conjecture, which I think we well, anyhow, we have a conjecture that something like the logarithmic integral. So this is ongoing work on trying to extend these things further and extend the Risch algorithm. But a conjecture would be that the logarithmic integral that you can't be integrated using any Abelian integrals. I'm sorry?
This isn't known.
I don't believe so. So I guess, yeah, we have ongoing work on this. I'm trying to extend Risch algorithm and trying to better understand the relationship between the Liouville theorem and Ax-Schanuel. So yeah, so I'm afraid I'm going to finish a tiny bit early. So that's all.
Okay, so do we have any questions for Jonathan?
Yeah, about the conjecture, what about the integral of E x squared?
Yes, I conjecture that 2, for sure.
Which one?
E to the x squared. This one looked more like a kind of iterated Abelian integral, right? Because you get log by integrating 1 over x, so then you've got log. This one seemed like slightly more natural fit in this picture. It's like a 2-step Abelian integral where you do an Abelian integral and then you integrate some algebraic function of that. Also, e to the x squared, you can sort of transform it. I mean, you can change your variables on these integrals and yeah, but I would think that too. But this is the one we were.
Can you see any measurement completely that makes this very simpler than do the X one?
Well, it's certainly, it looks like, log is the integral of 1 over x. This is the integral of 1 over log. It looked like the simplest thing to think about. Certainly, you'd ideally like to think about a much bigger picture where you have this kind of iterated Abelian integrals. I'd have to, I don't, so I didn't really, how can I put it? I think we've been thinking more about this one. E to the x squared, I forget exactly what you can transform it into.
They're almost the same, right? I think they should be also doable in the same way, because if you plug in x equals e to the y here, you get e to the y over y,
Right.
I think.
Yes.
And if you undo that with the x squared, it should be this thing with maybe an extra power of x or something. They should be almost the same thing, I think. Yeah.
Any other questions? You have the conjecture possibly 1 per meter elements.
No, no, I don't have such a conjecture. No, I mean, of course, you could then ask whether there was some kind of silver pink type picture of things sitting around there and some kind of arithmetic conditions. No. I guess we haven't really thought about parametric families.
I'd say would be exceptional.
Right.
The likely intersections are somehow. There's too many of those. I'm trying to make statements.
X some sort of like intersection, some sort of
Just from that. Interesting question. Yeah.
Any other questions? Okay, so let's thank Jonathan and Ed.